Welcome to G Fun Facts Online. Today, we're talking about a technology that sounds like it's straight out of a science fiction movie, but is very much a reality. Imagine building a complex jet engine part, not by carving it from a giant block of metal and wasting most of it, but by growing it from a cloud of fine metal powder, layer by microscopic layer. This is metal additive manufacturing, more famously known as metal 3D printing. It's a complete reversal of how we've made things for centuries. Instead of subtracting material away, we add it. This simple shift is sparking a revolution, moving from simple prototypes to full-scale factory production, and unlocking shapes and structures that engineers could previously only dream of. The technology has been around since the late 80s, but recent leaps in lasers, material science, and computing power have caused its growth to explode. So, let's dive into how we are literally forging the future, one layer at a time. The world of metal 3D printing isn't just one single technique. It's a whole family of sophisticated processes. The most common and precise method is called powder bed fusion, or PBF. Picture a sealed chamber filled with an inert gas like argon, to prevent the metal from rusting or oxidizing at high temperatures. Inside, a machine spreads an incredibly thin layer of fine metal powder across a build plate. Then, a high-energy source, either a powerful laser or an electron beam, zips across the powder, following a digital blueprint and melting the particles together. The platform then lowers by a fraction of a millimeter, a new layer of powder is swept across, and the process repeats. This happens thousands of times, until a solid metal object is fully formed, encased in a bed of loose, unfused powder. Within this PBF family, there are two main players. The first is selective laser melting, or SLM, and its close cousin, direct metal laser sintering, or DMLS. They both use high-powered lasers to fuse the powder. SLM fully melts the powder into a liquid, while DMLS heats it to the point where the particles fuse together on a molecular level without quite liquefying. For most purposes, the terms are used interchangeably. These techniques are famous for their incredible precision and ability to create parts with fine details. The mechanical properties of parts made this way can be as good as, or sometimes even better than, those made by traditional casting. The other major PBF technology is electron beam melting, or EBM. As the name suggests, it swaps the laser for a powerful beam of electrons, and it all happens inside a vacuum. EBM systems run much hotter than laser-based ones. This constant, high temperature acts like an oven, relieving internal stresses in the part as it's being built. This makes EBM perfect for tricky, high-performance materials that are prone to cracking, like titanium aluminide, which is used in the hottest parts of jet engines. EBM is generally faster than laser methods, but the trade-off is often a rougher surface finish that might need more post-processing. While powder bed fusion is great for precision, what if you need to build something huge or repair an existing part? That's where a different technology comes in: directed energy deposition, or DED. Instead of a bed of powder, DED uses a robotic arm with a special nozzle. This nozzle sprays a stream of metal material, either powder or wire, directly onto a surface. At the same time, a focused energy source, again a laser or an electron beam, melts the material right as it lands. You can use this to build a part from scratch, but it's also incredibly useful for adding features to an existing component, or for repairing high-value parts, like a damaged turbine blade, saving it from the scrap heap. Because it's not confined to a small, enclosed box, DED can create much larger parts. It's also generally faster than PBF. Now, what about mass production? Both PBF and DED are still relatively slow for making thousands of identical parts. This is where a third method, binder jetting, is set to change the game. Unlike the others, binder jetting doesn't use any heat during the printing step. Instead, it works more like a 2D inkjet printer. An industrial printhead glides over a bed of metal powder, precisely jetting a liquid binding agent, a sort of glue, to stick the powder particles together, layer by layer. This creates what's called a green part. This part is fragile, a bit like a sandcastle. After printing, the green part is carefully removed from the powder and placed into a high-temperature furnace. In this final step, called sintering, the binder is burned away, and the metal particles are heated to just below their melting point, causing them to fuse into a dense, solid metal object. The huge advantage of binder jetting is speed and scalability. You can use the entire powder bed to print dozens or even hundreds of parts at once. And because the loose powder supports the parts, you often don't need to print complex support structures. This makes it a promising pathway to high-volume, cost-effective metal manufacturing. So we have these incredible ways to print metal, but what exactly are we printing with? The palette of materials for metal AM is expanding rapidly. The materials are usually in the form of perfectly spherical, fine powders or specialized wires, designed to flow and melt predictably. Some of the most common materials include stainless steels, the workhorses of the industry, loved for their strength, corrosion resistance, and good price point. Then you have aluminum alloys, which are all about being lightweight yet strong, making them perfect for aerospace and high-performance cars. Titanium alloys are the superstars. They are incredibly strong, lightweight, corrosion-resistant, and biocompatible, meaning the human body doesn't reject them. This makes titanium the top choice for medical implants, like hip replacements and spinal cages, as well as critical aerospace components. For the most extreme environments, there are nickel-based superalloys, like Inconel. These materials can withstand incredibly high temperatures without losing their strength, which is why they are essential for parts inside jet engines and gas turbines. Other common materials include cobalt chrome for its wear resistance in dental and medical implants, and tool steels for printing custom tools and molds with incredibly complex internal features. You can even print with precious metals like gold and platinum, opening up a whole new world for custom jewelry design. Okay, we have the methods and the materials. Now for the most exciting part. What are industries actually doing with this power? The impact is staggering. In the aerospace and defense industry, every gram of weight saved means better performance and lower fuel costs. Metal 3D printing is a dream come true here. Engineers use software to perform topology optimization, which is a fancy way of saying they let a computer algorithm design a part by placing material only where it's structurally needed. The result is bizarre, organic-looking parts that are incredibly strong but impossibly lightweight. They are also using it for part consolidation. An assembly that used to be made of 20 different pieces bolted together can be redesigned and printed as a single, stronger, lighter part. This reduces weight, assembly time, and potential points of failure. Famously, NASA has stated it plans to 3D print over 80% of its future rocket engines. The medical and dental fields are experiencing a similar revolution, but this time it's all about personalization. Using data from a patient's CT or MRI scan, doctors can design and print a custom implant that fits that patient perfectly. This means better surgical outcomes and faster recovery times. Biocompatible titanium and cobalt chrome are used to print everything from hip and knee replacements to spinal cages and custom plates to repair skull injuries. The intricate, porous lattice structures that only 3D printing can create are a huge bonus for orthopedic implants, as they encourage the patient's own bone to grow into the implant, creating a stronger, more permanent bond. The automotive industry is also revving up its use of metal AM, especially in motorsport and luxury vehicles. It allows for the rapid creation of functional prototypes from final production materials, slashing development time. For high-performance cars, it's used to make lightweight, performance-enhancing components. But perhaps more importantly, it's revolutionizing the tools used to make cars. Companies are printing molds with something called conformal cooling channels. These are cooling lines that perfectly follow the shape of the part being made, something that's nearly impossible with traditional methods. This allows for faster cooling, which shortens production cycles and improves the quality of mass-produced plastic parts. This shift is happening for a few powerful reasons. The most important is unprecedented design freedom. Engineers are no longer limited by what a CNC machine can cut or what can be poured into a cast. If you can design it in a computer, you can probably print it. This freedom allows for the lightweight, topologically optimized parts and consolidated assemblies we just talked about. This leads to what is arguably the most tangible benefit: on-demand and customized production. Since there's no custom tooling required for each job, it's economically feasible to print a single, unique part. This is the key to personalized medicine and allows manufacturers to operate with digital inventories. Instead of stocking a warehouse full of spare parts that might never be used, a company can simply print a part when it's needed, drastically shortening supply chains. Finally, there's a sustainability angle. Traditional subtractive manufacturing is incredibly wasteful. You might start with a 100-kilogram block of titanium and machine it down to a 10-kilogram part, turning 90% of that expensive material into scrap. As an additive process, 3D printing uses only the material needed for the part, generating significantly less waste. This saves money and reduces the environmental footprint of manufacturing. Of course, the path to a fully 3D printed world isn't without its bumps. The technology still faces some significant challenges. First is the cost. Industrial-grade metal printers are expensive, and so are the specialized metal powders they use. This high barrier to entry keeps it out of reach for many smaller businesses. Quality control is another major hurdle. When you're making a critical part for a passenger airplane or a medical implant, you need to be 100% certain that every single part is perfect. Ensuring that consistency down to the microscopic level is a huge focus of research right now. Developing robust industry standards and certification processes is crucial for these safety-critical applications. Furthermore, parts are rarely ready to use straight out of the printer. They almost always require post-processing. This can include heat treatment to relieve stress, cutting the part off the build plate, removing support structures, and then machining or polishing surfaces to get the exact tolerances and smoothness required. These extra steps add time and cost to the process. But the future for metal additive manufacturing looks incredibly bright. Researchers are working tirelessly to overcome these challenges. We're seeing the integration of artificial intelligence and machine learning into the workflow. AI can help optimize designs for printability, monitor the build process in real time to predict and correct errors before they happen, and automate quality control. We're also seeing the rise of hybrid machines that combine additive printing and subtractive CNC machining in one platform. These machines can print a part and then immediately machine the critical surfaces to a perfect finish, all without having to move the part. And as printing speeds get faster and costs come down, we're seeing the most important shift of all: the move from prototyping to true serial production. Companies are no longer asking, "Can we 3D print this part?" They're starting to design products from the ground up with an additive-first mindset. In conclusion, metal 3D printing has evolved far beyond a niche tool for making plastic trinkets and prototypes. It is a powerful, industry-disrupting force that is fundamentally altering how we create high-value functional metal parts. By building objects layer by layer, it allows us to create stronger, lighter, and more complex components than ever before. It's driving a new wave of innovation, efficiency, and personalization across our most critical industries. While challenges remain, the pace of progress is undeniable. The rise of 3D printed metals isn't just a fleeting trend. It is the forging of a new foundation for the future of manufacturing. Thanks for listening to G Fun Facts Online.